Hello everyone, thank you for watching our first video blog. Many drivers know that crashing is a part of racing, so today we'll be talking about our incident at Pikes Peak and Bottomless Pit and talk about the safety gear, how it worked, what it did, and what to do next. After the wreck, we spent some time researching information. We found some stuff online, but we were still greatly faced with the question of, we crashed, now what? The first thing that you notice is that the passenger side A-pillar is pushed down. None of the tubes were kinked, but it was interesting to follow the trend of flaking paint at the points that experienced higher strain. So keep an eye out for those areas and inspect the welds around them. Even though the safety belts keep you from going through the windshield, they don't have much for side-to-side support. So in the event of a side impact, the seat brackets actually take quite a bit of force. Back when Zach Fothergill and I were building the cage, I had modeled the structure up for my finite element analysis class at the University of Colorado at Boulder. FEA is a numerical way to study smaller bits of a large problem. After looking over the actual structure from the crash, I was fascinated by how similar the outcome was to the analysis I had done. The professor always says that you must verify your results with a test, so here we are. The analysis showed that A-pillar reinforcement bars would be highly recommended. Now, the only reason that Zach and I didn't install those was because we had spec'd out a larger size tubing and we were worried about the ease of getting in and out of the car. Now, many assumptions have to be made to simplify the model. The analysis performed was never intended to show how much displacement the cage would experience or anything of that. It was merely to show the difference between two designs. So today, I would like to use real-life data to compare the results of our specific crash to what would have happened if we had A-pillar reinforcement bars at Pikes Peak. There are still many unknowns. We don't know how the body shell affects the overall strength, how much force was applied at the impact. All we know is the final deformation of the tubes after they sprung back. So, to avoid making any unrealistic assumptions, we will simplify the model by looking at only the elastic properties of the material, assuming complete spring back, and figure out how much force it would take to displace the top of the A-pillar by the measure 21 millimeters, and then apply the same force to a modified design and compare the displacements. As you can see, the model is simplified to a freestanding roll cage structure. The bend radii are simplified, and the force is applied to the top of the passenger side A-pillar. Now watch the same scenario with the added reinforcement bar. The structure does a much better job of distributing the stress, and the displacement is reduced to only 4 millimeters compared to the initial 21 millimeters. This is not a DOT certified crash test. It is a simple analysis performed to show the effect of an A-pillar reinforcement bar. In our case, with a fifth of the displacement of the cage, it could very well have not deformed and we would be in a much better position in fixing the car. So please use this information for yourself when deciding what kind of cage design to go with, what to include, what not to include. But just keep in mind that the FIA specs require the A-pillar reinforcement bars, and for good reason. Thank you for watching. We'll be back, and we hope to see everybody at the track soon.